What if reality is nothing like what it seems? We are about to journey through 50 astonishing theories on the nature of existence itself. From ancient philosophies questioning the solid ground beneath our feet to modern physics suggesting we live in a cosmic simulation, this exploration will challenge your most basic assumptions about the universe. By the end, you will possess a panoramic view of reality's greatest mysteries and the boldest attempts to solve them. We will confront whether our world is a hologram and if every choice spawns a parallel universe. What single question about reality have you always been afraid to ask? Our very first theory begins with a question that has captivated philosophers and scientists alike. What if everything we perceive as reality is in fact an intricate digital construct, a simulation running on a computer of unimaginable power? This is the simulation hypothesis, a modern argument with ancient roots. The philosopher Nick Bostrom offered a compelling logical framework for this idea. He suggests that one of three propositions is almost certainly true. Either civilizations like ours go extinct before reaching a post-human stage capable of running simulations, or advanced civilizations have no interest in running ancestral simulations, or we are almost certainly living in one. Given the vast number of potential civilizations across cosmic history, the sheer number of simulated realities would vastly outnumber the one base reality. This mathematical probability is a core reason why influential thinkers like Elon Musk find the theory so convincing. He has famously argued that the odds we are in base reality are just 1 in billions. But what about evidence? Proponents sometimes point to what they call glitches in the matrix, strange phenomena that defy conventional explanation. These could be anything from déjà vu, that eerie feeling of having already experienced the present moment, to seemingly random quantum behaviors that mirror the processing shortcuts a computer might take to conserve resources. The idea forces us to look at the very fabric of our world with new eyes. If this is a simulation, then the laws of physics are not fundamental truths, but merely the underlying code of the program. If the world is a simulation, then the very nature of our own consciousness comes into question. Are our thoughts and feelings genuine, emergent properties of a complex biological brain, or are they simply lines of code, sophisticated algorithms designed to mimic self-awareness? This leads to a startling ethical dilemma. If we are simulated beings, what responsibility do our creators bear for our suffering and our joy? Are they mere programmers observing data, or are they gods in a digital universe accountable for the pain written into their creation? This theory also radically reshapes our understanding of free will. Your choices might feel entirely your own, but they could be predetermined by the initial conditions of the simulation, or the result of random number generators creating an illusion of spontaneity. What then becomes of purpose and meaning? Does a life lived inside a construct have less value than one in base reality? Perhaps the answer is no. The love we feel, the beauty we perceive, and the connections we forge remain real to us regardless of their ultimate substrate. The search for meaning might then become internal, a personal journey within the confines of the program, making our experiences no less profound. Yet if our reality is a simulation, what is the nature of the projector? A second, equally radical theory suggests the universe itself is a cosmic hologram. The holographic principle proposes that everything we perceive in 3 dimensions, from the farthest galaxy to the feeling of your own hand, is actually a projection from a 2-dimensional surface at the edge of the cosmos. This is not science fiction, but a serious framework born from the study of black holes. Physicist Leonard Susskind and others made a startling discovery when examining how information behaves at a black hole's boundary, its event horizon. They found that the maximum amount of information that can be stored in any region of space is not proportional to its volume, as you might expect, but to the area of its surface. Imagine a movie. The three-dimensional action you see on the screen is encoded on the two-dimensional film strip running through the projector. In the same way, our rich, three-dimensional reality might be entirely encoded on a distant, two-dimensional boundary that surrounds us. This principle elegantly bridges a fundamental conflict in physics: quantum mechanics, which rules the very small, and general relativity, which governs gravity and the very large, have been famously at odds for a century. The holographic principle can resolve this by suggesting that gravity itself emerges from the complex quantum interactions happening on that flat, informational surface. We are, in a sense, living inside a projection, a cosmic shadow play where depth is an illusion. But the holographic universe still leaves us with just one cosmic story. What if every possible story is being told at once? This is the mind-bending promise of the many worlds interpretation of quantum mechanics. In the tiny realm of atoms and particles, things behave in famously strange ways. An electron is not in one place but exists in a blur of probability, a superposition of many possible locations. Traditional physics said that the moment we observe this electron, its wave function collapses, forcing it to pick a single, definite location. Physicist Hugh Everett asked a simple, radical question: what if that collapse never actually happens? He proposed that every single possible outcome of a quantum event does occur, but in a newly branched parallel universe. At the moment of measurement, reality itself splits. In one universe, you see the electron on the left. In another, an identical version of you sees it on the right. This branching is not a rare event. It happens constantly with every quantum decision, every random fluctuation, creating an infinite and ever-growing multiverse. There is a universe where you never watched this video, and another where you are already an expert on cosmic mysteries. This interpretation solves one of quantum theory's biggest puzzles by removing the seemingly magical collapse of the wave function. The universe does not choose, it simply realizes every option. The flow of time, then, is not a river with a single course, but an endlessly dividing delta, with each stream representing a complete and valid reality. This means that every choice you have ever made, and every choice you did not make, is being lived out in full somewhere else. The multiverse is not a distant collection of alien landscapes, but a proliferation of worlds nearly identical to our own, differing only in the outcome of a single quantum coin flip. It presents a cosmos of infinite possibilities where nothing is ever truly lost, only separated by an unbridgeable divergence in the fabric of existence. Yet the idea of infinite branching worlds raises a profound question about the very substance of reality. What are these parallel universes and ours ultimately made of? String theory offers one of the most ambitious answers, proposing that the fundamental ingredients of the cosmos are not point-like particles, but unimaginably small, vibrating loops of energy. Think of the strings on a violin. A cello string vibrates to produce a deep, rich note, while a tightly stretched violin string creates a high, sharp pitch. In string theory, every particle in nature is just a different resonant frequency of these same fundamental strings. An electron is one vibrational pattern. A quark is another. The photon that carries light is simply a string vibrating in a specific way. This elegant idea promises to be the ultimate unifying principle, a potential theory of everything. It elegantly weaves together the force of gravity, described by Einstein's general relativity, with the bizarre quantum rules that govern atoms. For the first time, one framework could explain all forces and all matter. But this beautiful simplicity comes with a staggering cost. The mathematics of string theory only works if the universe has more than the three spatial dimensions and one time dimension we experience. It requires a cosmos of 10 or even 26 dimensions, all curled up and hidden from our perception. Imagine a garden hose viewed from a great distance. It looks like a simple one-dimensional line, but an ant crawling on its surface would experience a second dimension circling the hose's circumference. In the same way, these extra dimensions could be compactified, curled into shapes so tiny that we simply cannot detect them. This grand vision, however, remains just that, a vision. After decades of work, string theory has yet to make a single prediction that can be tested with our current experiments. Its mathematical complexity is so immense that even its practitioners struggle to find unique solutions, leading some critics to question if it is a true scientific theory at all, or an intricate and beautiful piece of metaphysics. It stands as a majestic cathedral of thought, a testament to our desire for a final answer, but one whose doors remain, for now, firmly locked. Our intuitive sense of time as a flowing river is a powerful illusion. Special relativity paints a very different picture, one where the past, present, and future are all equally real, frozen together into a single, four-dimensional structure known as the block universe. In this view, your birth, your life, and your eventual end are not events that come into being and fade away. They are all permanently fixed within this cosmic block, like frames in an immense, unchanging film reel. Einstein's own theories lead us directly to this startling conclusion. He showed that time is not absolute, but is relative to an observer's motion. Two events that are simultaneous for one person may not be for another who is moving at a different speed. This shatters the idea of a universal present moment that sweeps across the cosmos. What is real must be the entire, unchangeable history of the universe, from the Big Bang to the farthest future. You are not moving through time. You are simply extended along it, with your consciousness creating the persistent feeling of a present moment that slides from one frame to the next. Think of a long road you are driving down. The towns you passed, the town you are in now, and the towns you will visit tomorrow all exist simultaneously along the road's length. You experience them sequentially because you are traveling, but the road itself is complete and unchanging. This is the block universe. Your entire life is already written, not by fate, but by the geometry of space-time itself. This challenges our deepest feelings about free will and the passage of time. If the future is already out there, just as real as the past, then what does it mean to make a choice? The block universe theory does not say our decisions are meaningless. It suggests that our conscious experience of deliberating and choosing is an integral part of the block's fixed structure. You are not a puppet on a string, but a character whose entire story, including every thought and decision, is part of the timeless whole. This eternalist view forces us to confront a cosmos far grander and more static than our fleeting perceptions allow, a reality where every moment that ever was or will be is forever now. A starkly different perspective turns the material world entirely on its head. Perhaps the universe is not made of matter at all, but is instead a vast, interconnected network of mind. This is the heart of idealism, a philosophy that insists reality is fundamentally mental. Its roots run deep from Plato's realm of perfect forms, which he considered more real than the shadowy physical world, to the ancient Eastern traditions of Buddhism and Hinduism, which have long taught that the perceived world is an illusion or maya, veiling a unified conscious reality. The modern world, steeped in science, largely assumes the opposite, that consciousness is a byproduct of the brain, an emergent property of complex neural computations. The idealist flips this script completely. Matter is not the foundation, but the appearance. What is truly fundamental is consciousness itself. Contemporary thinkers like Bernardo Kastrup present a compelling case for this view. He argues that the seemingly solid world we perceive is the outer manifestation of a deeper, universal mind, much like a dream is the visible expression of our own subconscious. In this framework, your individual consciousness is not generated by your brain. Instead, your brain is more like a filter, a localized receiver that translates the infinite field of universal consciousness into the specific, personal experience you call yourself. This elegantly sidesteps one of the most difficult problems in science, the so-called hard problem of consciousness. How can subjective experience, the rich red of a sunset or the ache of sadness, arise from purely objective, unfeeling matter? For the idealist, this is not a mystery to be solved, but a false question. Consciousness does not emerge from matter because consciousness is what is primary. Matter emerges from it. The cosmos is not a dead, mechanical clockwork, but a living, thinking process. You are not a ghost in a machine. You are a whirlpool in a vast ocean of mind, temporarily individuated but never truly separate from the whole. Your reality is, in the most literal sense, all in your head, because your head and everything else is already in mind. But this cosmic ocean of mind stands in stark opposition to our everyday experience. Most of us live our lives under the assumption that the physical world is the only real world. This bedrock belief is known as materialism, the dominant scientific worldview for centuries. It posits that everything in the universe, including our thoughts and feelings, is ultimately composed of physical matter and energy interacting according to fixed laws. From the orbit of planets to the firing of neurons in your brain, materialism sees reality as a vast, complex, but ultimately mechanical system. Its greatest strength is its immense explanatory power. This framework has given us modern medicine, chemistry, and our understanding of genetics, all by meticulously studying the physical processes that underpin life. When a neurosurgeon maps the brain, they can point to specific regions that light up with activity when you feel love or fear or recognize a face. The materialist argument is compelling. Alter the physical brain with chemicals or injury, and you directly alter the mind. The mind, therefore, seems to be what the brain does, an emergent property of its intricate biological machinery. Yet for all its successes, materialism faces one monumental and unresolved challenge, the hard problem of consciousness. Science can explain how the brain works, how it processes information and governs behavior. But it cannot explain why or how any of this physical activity gives rise to subjective experience itself. Why should a particular pattern of neural firing feel like the stunning crimson of a sunset? Why does the processing of damaged signals result in the raw, unpleasant quality of pain? The physicalist can describe the entire chain of events in the brain, but the inner experience, the what it is like to be you, remains utterly absent from that description. It is like trying to understand the plot of a movie by only studying the chemistry of the film strip. You can know everything about the physical substrate and still have no grasp of the story being told. This profound gap suggests that our understanding of reality may be incomplete, that the physical world, for all its solidity, might not be the whole story. Materialism and idealism seem to present us with an impossible choice between a world without inner life and a world made of mind. But a third path offers a radical compromise. Panpsychism proposes that consciousness is not an emergent property of complex brains, nor is it exclusive to a universal mind. Instead, it is a fundamental and ubiquitous feature of the universe, present in every piece of matter, no matter how small. The word itself comes from the Greek pan, meaning all, and psyche, meaning soul or mind. This is not the childish idea that rocks are happy or electrons are sad. It is the sophisticated proposal that some form of incredibly basic, raw experience is a fundamental property of physical reality, just like mass or charge. Philosopher David Chalmers has been a prominent voice for this view, arguing it may be the only way to solve the hard problem of consciousness. His reasoning is elegant. If you assume that consciousness magically appears only when matter reaches a certain, unspecified level of complexity, you are left with an arbitrary and unexplainable leap. How and why does complex organization suddenly produce subjective feeling? Panpsychism avoids this magic trick by suggesting that consciousness was always there, a fundamental building block of nature. In this view, the fundamental constituents of reality, perhaps electrons or quarks, possess a minute amount of proto-consciousness. They have a simple, isolated point of view, an experience so elementary we can scarcely imagine it. When these particles combine into more complex systems, their individual conscious experiences combine as well. The human brain, with its trillions of neurons and quadrillions of connections, does not create consciousness from nothing. It orchestrates and unifies these fundamental bits of consciousness into the rich, complex stream of awareness you experience right now. Think of each fundamental particle as a single musical note. Alone, it is a simple tone, but when billions of these notes are combined in the intricate structure of a symphony orchestra, they produce a profound and beautiful experience of music that could never be found in any single note. Your mind is that symphony. This perspective elegantly bridges the explanatory gap, placing consciousness inside the physical world from the very beginning, rather than treating it as an awkward afterthought. It suggests a universe that is not dead, but tingling with an inner life at every level, a cosmos where we are not strangers, but deeply connected participants in a conscious reality. The idea that consciousness is woven into the fabric of the cosmos takes an even more active turn. We may not just be living in a conscious universe, we might be the very reason it exists at all. This is the participatory anthropic principle, a mind-bending proposal from physicist John Archibald Wheeler. He suggested that the universe only comes into a definite state when it is observed by a conscious being. In this radical view, we are not merely passive spectators, we are active participants co-creating reality through the very act of looking at it. The evidence for this astonishing idea comes from the heart of quantum mechanics, particularly the famous double-slit experiment. When tiny particles like electrons are fired one by one at a barrier with two slits, they behave in a way that defies common sense. If no one is watching, each electron seems to pass through both slits at once, like a spread-out wave, and interferes with itself on the other side to create a distinctive pattern. But the moment a detector is placed to observe which slit an electron goes through, its behavior changes instantly. It acts like a single, solid particle, choosing one slit, and the interference pattern vanishes. The simple act of measurement, of asking a question of the universe, forces a definite outcome. Wheeler took this further with his delayed choice experiment, a cosmic version of this quantum weirdness. Imagine light from a distant quasar, a brilliant galaxy, bending around a gravitational lens on its billion-year journey to Earth. We can set up an experiment to detect if that light traveled as a particle, taking one path, or as a wave, taking both paths. Our choice today, right now, seems to determine what that photon did a billion years in the past. The universe, it appears, does not have a fixed history until it is observed in the present. We are not just reading the book of reality, we are writing it with every glance. This principle places an immense responsibility on the observer. Without a conscious mind to crystallize possibilities into facts, the universe would remain a ghostly realm of potential, a haze of what might be. Your attention is not a minor detail in a vast cosmos. It is the very mechanism that brings the cosmos into sharp focus, turning a symphony of probabilities into the solid world you call home. If our observations bring the universe into being, what shaped its laws to be so perfectly tuned for life in the first place? One daring answer suggests that our cosmos is not a unique creation, but the product of a grand evolutionary process. Physicist Lee Smolin proposed the theory of cosmological natural selection, a breathtaking idea where universes reproduce and evolve. Just as life on Earth adapts through natural selection, Smolin theorized that the cosmos itself might be subject to the same creative mechanism. The engine of this cosmic evolution is the black hole. In Smolin's framework, every time a black hole collapses at the center of a universe, it does not simply vanish into a singularity. Instead, it becomes the seed for a new Big Bang, giving birth to an entirely new universe inside itself. This new cosmos exists in its own space-time, disconnected from its parent, yet it inherits its fundamental physical constants. But the inheritance is not perfect. Just as DNA replication in biology occasionally introduces mutations, the process of universe creation introduces tiny, random variations in the laws of physics. One daughter universe might have a slightly stronger gravitational constant, while another might have a different strength for the nuclear forces. Most of these mutant universes would be stillborn or barren. If the gravitational constant were too strong, stars would burn out in a cosmic flash, never giving planets time to form. If the nuclear forces were weaker, hydrogen would never fuse into heavier elements, leaving the cosmos with no carbon, no oxygen, and no chemistry of life. But a rare few of these new universes, by pure chance, would have constants even more finely tuned for the creation of stars, planets, and ultimately, life. And here is the brilliant evolutionary twist. Those life-friendly universes are precisely the ones that produce the most black holes. Stable, long-lived stars that forge the elements of life are the same stars that eventually collapse into black holes. Therefore, a universe that is good for life is also, inevitably, a universe that is highly prolific in cosmic reproduction. Over countless generations, through this process of cosmological natural selection, the multiverse becomes dominated by universes whose physical laws are optimized for making black holes, which, as a fortunate byproduct, are also the laws that allow us to exist. We do not live in a miraculously fine-tuned universe. We live in a fertile one, a cosmic ancestor in an immense family tree of universes, whose very laws were shaped by the relentless drive to reproduce. This evolutionary struggle among universes suggests that the laws of physics are not divine commandments, but contingent outcomes. Yet one physicist pushes this logic to its ultimate, breathtaking extreme. Max Tegmark's mathematical universe hypothesis proposes that our physical reality is not just described by mathematics, it is mathematics. We are not living in a universe that happens to follow mathematical rules. We are living inside a mathematical structure itself. Think of a triangle. It has a set of immutable properties and relationships defined by geometry. It does not exist in space, it defines a kind of space. Tegmark argues our cosmos is just like that, but vastly more complex. Every object, every force, every particle is ultimately a mathematical entity interacting according to mathematical rules. The equations are not a map of the territory, they are the territory. This leads to an even more radical corollary. If reality is purely mathematical, then every self-consistent mathematical structure must exist with the same physical reality as our own. Our universe, with its specific set of equations governing quarks and cosmos, is just one entry in the vast library of all possible mathematical structures. Some of these other mathematical worlds would be barren, containing only empty sets or simple geometric shapes. Others would be teeming with complexity, perhaps governed by laws where time has two dimensions or gravity is repulsive. In this view, mathematicians are not inventors creatively constructing abstract worlds. They are explorers, discoverers, charting the contours of a pre-existing abstract landscape. When Pythagoras derived his theorem, he was not creating a new truth. He was uncovering a permanent feature of a reality that was always there, waiting to be found. This completely inverts our understanding of existence. It suggests that the abstract, timeless world of numbers and shapes is the primary reality, and our physical, experiential world is a secondary manifestation. The solidity of your chair and the warmth of the sun are just your brain's particular way of experiencing a specific, complex mathematical relationship. The universe does not have a designer, it has a definition. And we are living proof that one of those definitions is rich enough to contain conscious, self-aware substructures that can look back upon the equations and wonder, are we the universe discovering itself? This endless multiplication of mathematical realities finds a powerful echo in the cosmos itself. Eternal inflation paints a picture of a reality so vast it defies human comprehension, suggesting our entire universe is merely a single bubble in an infinite, frothing sea of cosmic foam. The theory begins with the well-established concept of cosmic inflation, the idea that in the first fraction of a second after the Big Bang, our universe underwent an exponential, faster-than-light expansion, smoothing it out and creating the large-scale structure we see today. Eternal inflation proposes that this inflationary process never truly stopped. Instead, it continues eternally in a background meta-universe, a roiling, high-energy state sometimes called the inflaton field. Within this chaotic field, random quantum fluctuations cause pockets to drop out of the inflationary phase, much like bubbles forming in a pot of boiling water. Each time this happens, the energy driving inflation is released in a cataclysmic flash, creating a hot Big Bang and giving birth to a new, isolated universe or a pocket universe within the greater multiverse. Our cosmos is just one such bubble, one island universe in an endless archipelago. The evidence for this staggering idea is written in the oldest light we can see, the cosmic microwave background radiation. Precise measurements of this faint afterglow from the Big Bang reveal a universe that is remarkably flat and uniform on large scales, exactly the signature you would expect from a past period of rapid inflation. The tiny temperature variations in this background radiation are thought to be the quantum seeds, magnified by inflation, that eventually grew into all the galaxies and clusters we observe today. The implication is that inflation is a perpetual engine of creation. While our local bubble stopped inflating, the greater meta-universe continues to expand at an unimaginable rate, constantly spawning new bubble universes, each with its own potentially unique set of physical laws and constants. Some of these bubbles might have stronger gravity, collapsing instantly into black holes. Others might have weaker nuclear forces, never forming atoms. We exist in one of the rare, stable bubbles where the laws of physics allowed for stars, planets, and life to emerge. The ultimate scale of reality, therefore, is not just vast in space, but vast in possibility, a truly infinite multiverse where every conceivable physical law is realized somewhere in the eternal froth. Yet this infinite cosmic foam presents a paradox so unsettling that it threatens to unravel our very sense of self. In a universe destined for maximum disorder, a random fluctuation can momentarily create order from chaos. Given enough time, a state of perfect equilibrium known as heat death, even the most improbable things become not just possible but inevitable. This is the foundation of the Boltzmann brain paradox, a thought experiment that turns our origin story into a statistical nightmare. The physicist Ludwig Boltzmann first suggested that our entire observed universe, in all its beautiful order, might be a rare but temporary random fluctuation in a cosmos that is mostly a featureless, high-entropy soup. The modern version of this idea takes this logic to its terrifying extreme. If the cosmos is eternal or infinitely large, then the random, spontaneous assembly of a fully formed, self-aware brain, complete with a lifetime of false memories and sensory impressions, is statistically far more likely than the slow, laborious process of biological evolution. Think of a tornado ripping through a junkyard and accidentally assembling a fully functional jet engine. Now imagine that happening not with metal but with atoms, and the engine is a conscious mind. The Boltzmann brain paradox suggests that you, with all your memories and your feeling of a continuous past, are almost certainly such a momentary accident. You did not evolve on a planet over billions of years. You just popped into existence a moment ago, a lone, disembodied brain floating in the void, hallucinating an entire reality from the Big Bang to this very sentence before dissolving back into chaos. The sheer improbability of our vast, structured cosmos makes it a less likely random fluctuation than a single, isolated observer. This means we should statistically expect to be Boltzmann brains, not evolved beings in a grand universe. The fact that we perceive a coherent, consistent world around us is the very evidence that this paradox might be true, because a hallucinating brain would be programmed to perceive exactly that. It is a cosmic catch-22 that leaves us questioning whether we are enduring entities or fleeting statistical ghosts. While the Boltzmann brain suggests we might be cosmic accidents, other theories place our own perspective at the very core of reality. Quantum Bayesianism, or QBISM, turns the traditional interpretation of quantum mechanics completely on its head. It proposes that the probabilities at the heart of quantum theory are not objective features of the world, but are instead deeply personal. They represent an agent's own subjective degrees of belief, a measure of personal uncertainty about what will happen in a future experiment. In this view, quantum mechanics is not a description of an independent, observer-independent reality. It is a user's manual, a tool that helps a conscious agent navigate the world and update their expectations based on what they experience. The famous wave function, that mathematical entity that describes a particle state, does not physically exist out in the world. According to QBISM, the wave function is not a picture of the particle itself. It is a compendium of the beliefs held by the agent making the measurement. It resides entirely within the user's mind. When you perform a quantum experiment and get a specific result, you are not causing a wave to collapse out in the universe. You are simply updating your own internal information, your own personal betting odds about what will happen next. Imagine you are about to flip a coin that you know is perfectly fair. Before the flip, your personal probability for heads is 50%. This 50% is not a property of the coin. It is a statement about your own knowledge and expectations. The moment you see the coin land, that probability instantly updates to 100% for heads or 0% for tails. QBISM treats all quantum probabilities in exactly this way. The strange quantum jumps and collapses are not physical events, but mental ones, reflecting the moment an agent gains new information and changes their mind. This makes every measurement outcome a unique, personal experience for the observer who makes it. Your reality is not the same as my reality because your beliefs and your experiences are your own. QBISM dissolves the paradox of Schrödinger's cat by stating the cat is never both dead and alive. The wave function describing the superposition is just a tool in the physicist's notebook, representing their uncertainty before they open the box. The cat itself is always in one definite state, and opening the box simply reveals that state to the observer, who then updates their personal catalogue of beliefs. This intensely subjective approach reframes our entire quest to understand the cosmos. We are not discovering a pre-written script of reality. We are each writing our own, one personal measurement at a time. This strange intimacy between observer and observed suggests that time itself may play a more active role than we ever suspected. The transactional interpretation of quantum mechanics offers a truly radical vision where reality is forged through a kind of handshake across time. Proposed by physicist John Cramer, this theory suggests that every quantum event involves waves traveling both forward and backward in time, meeting in the middle to seal a deal. Imagine you want to send a radio signal. You transmit an offer wave outward in all directions and forward in time. When that wave encounters an absorber, like a radio receiver tuned to your frequency, it sends a confirmation wave back through time to the exact moment and location of the original transmission. It is this handshake, this completed transaction between the advanced wave from the future and the retarded wave from the past, that makes a real, definite event happen. In this view, the probabilistic nature of quantum mechanics is not a sign of fundamental randomness, but a reflection of the many possible transactions that could be completed. An electron does not magically jump from one orbit to another. It sends out offer waves for all possible destinations. The atom receiving the energy then sends confirmation waves back, and the strongest handshake, the one that resonates most perfectly, wins out, becoming the actualized event we observe. This elegant process provides a clear, physical picture for the collapse of the wave function without needing to invoke countless splitting universes. The entire history of a quantum system is a single, self-consistent loop where the future helps to create the past that leads to it. It is a cosmic dance of cause and effect, where the effect reaches back to finalize its own cause, locking reality into a single, definite story. The transactional handshake across time suggests a cosmos running on a kind of logic. This leads to a theory where the universe itself is the ultimate computer. Digital physics proposes that reality is not made of smooth, continuous fields, but is fundamentally discrete and computational, running on a cosmic substrate of bits. The pioneers of this idea, like Edward Fredkin and Konrad Zuse, argued that the universe is essentially a giant cellular automaton. Imagine a vast, three-dimensional chessboard extending through space and time. Each square on this board is a cell that can be in one of a finite number of states, like on or off. The entire cosmos ticks forward in discrete steps like the frames of a movie. At each tick, every cell updates its state based on a simple set of rules and the states of its neighboring cells. From these incredibly simple local interactions, the immense complexity of galaxies, life, and consciousness emerges. The flowing water in a river is not a continuous substance, but the collective behavior of countless tiny cells following their rules. A thought in your mind is a specific, intricate pattern of states flashing across this cosmic grid. Konrad Zuse, one of the inventors of the modern computer, was the first to seriously propose that the universe is being computed on a gigantic cellular automaton. Edward Fredkin took this further, suggesting that the laws of physics are not primary, but are themselves emergent properties of the underlying computational process. In this view, what we call an electron is just a stable, self-replicating pattern of information, a glider in the cosmic game of life. The theory naturally incorporates a discrete fabric for space and time, solving the baffling infinities that plague theories of quantum gravity. It paints a picture of a cosmos that is not just described by mathematics, but is actively calculating itself into existence, one Planck-sized time step at a time. This transforms the universe from a static object into a dynamic process, a computation whose output is reality itself. And if the cosmos is a computer, it forces us to ask a profound question. Who or what is the programmer? The strange allure of quantum theory is that it refuses to give us a single answer. The many worlds interpretation is just one of several compelling visions for how a world of probability becomes the world we see. Another fascinating path is the modal interpretation, which makes a subtle but profound distinction. It suggests that quantum possibilities are not just mathematical abstractions, but real, physical properties of a system. In this view, an electron truly is in a superposition of states, possessing all its possible properties at once, even before we measure it. The act of measurement does not create a branching universe. Instead, it simply reveals which one of those pre-existing properties we happen to see. Think of a spinning coin. While it is in the air, it genuinely possesses both the property of being heads and the property of being tails simultaneously. It is not that one outcome is real and the other is not. Both are equally real aspects of the spinning coin state. When it lands, you do not create a heads outcome universe. You simply discover which face was facing up at the moment of contact. The modal interpretation treats the quantum world in a similar way, preserving all the weirdness of superposition while keeping our reality singular. It gives a kind of substance to possibility itself, suggesting that what might be is just as fundamental as what is. Yet another school of thought, the consistent histories approach, sidesteps the problem of observation entirely. It argues that we ask the wrong question by focusing on a single, instantaneous measurement. Reality, it claims, is not about isolated events, but about entire stories or histories that we can tell about a system. A history is a sequence of events over time. The theory then provides a logical framework to decide which of these potential stories are consistent with the rules of quantum mechanics and can therefore be considered to have truly happened. In this view, it is meaningless to ask which slit a single electron went through. That question does not belong to a consistent, tellable history. The only consistent story you can tell is one where the electron behaved as a wave, went through both slits, and created an interference pattern. The moment you place a detector at a slit, you change the set of questions you are allowed to ask. Now, the only consistent history is one where the electron went through one specific slit like a particle. The universe is not a single timeline, but a tapestry of all possible, self-consistent narratives. We do not cause one history to become real by looking. We simply choose which set of consistent histories we wish to discuss, and our reality is the one woven from those threads. It is as if the cosmos is a grand library, and our experiments are us selecting which volume from the shelves we want to read. Each of these interpretations offers a different resolution to the quantum riddle, presenting a unique multiverse of possibility. Many worlds gives us a literal infinity of branching worlds. The modal interpretation gives us a single world where possibility has a tangible, physical reality. Consistent histories gives us a world defined by the logical coherence of the stories we can tell about it. They all start from the same mathematical equations, the same experimental results, yet they paint wildly different pictures of the nature of existence. This is not a sign of a broken theory, but a testament to its profound depth. Quantum mechanics may be less a description of reality and more a doorway into it, a set of rules that reveals just how much our classical intuition fails when faced with the fundamental layer of the cosmos. The very fact that we can entertain such divergent, yet logically sound, visions of what is real suggests that the universe is far stranger and more malleable than our senses could ever perceive. Our own minds might be a perfect example of a holographic reality in action. The holographic brain theory, developed by neuroscientist Carl Pribram, proposes that your brain itself functions like a hologram. This idea emerged from a puzzling mystery in neuroscience. For decades, researchers tried to map memories to specific locations in the brain, but the results were baffling. No matter which small section of a rat's brain they removed, the memory of a complex maze could not be entirely erased. It was as if the memory was stored everywhere at once, and any piece of the brain could access the whole. Pribram realized this was eerily similar to how a hologram works. If you shatter a piece of holographic film, any single fragment can still reconstruct the entire three-dimensional image, though with less clarity. The image is not stored in one spot. It is distributed across the entire surface, with each part containing information about the whole. Pribram suggested the brain does the same with memory and perception. Instead of having a dedicated filing cabinet for your grandmother's face or the smell of rain, your brain stores these memories as intricate interference patterns spread across the vast network of neurons. When you recall your grandmother, your brain does not retrieve a single file. It illuminates the entire holographic plate, reconstructing the memory from the distributed pattern. This elegantly explains the brain's immense storage capacity, as a hologram can hold a staggering amount of information in a very small space. But the theory goes even further, potentially explaining the very nature of conscious experience. The world you perceive, with its rich textures and vivid depth, may not be a direct readout of sensory data. Your brain could be interpreting frequencies from a deeper, holographic realm, translating them into the solid, three-dimensional reality you navigate every day. You are not just looking at a holographic universe, you are a walking, talking holographic projector constantly creating the world you call real. The stark finality of the block universe stands in direct opposition to our most powerful intuition, the feeling that only the present moment is genuinely real. This conviction, known as presentism, argues that the past is gone forever and the future is not yet born. All that exists is the fleeting, razor-thin slice of time we call now. The chair you are sitting on, the sound of these words, the thoughts in your head, they are all real precisely because they are happening in this immediate present. Everything else, from the fall of the Roman Empire to your next breath, is either a memory or a possibility lacking concrete existence. Presentism aligns perfectly with our lived experience. It feels true. We mourn the past because it is lost, and we anticipate the future because it has not yet arrived. This view makes change a fundamental and real process, as objects truly gain and lose properties over time. A candle is whole, then it is melted. The whole candle ceases to exist, replaced by a new state of affairs in the present. Causality also feels straightforward, a chain of events where the present state is directly caused by a previous present state that no longer exists. Yet for all its intuitive appeal, presentism faces a devastating challenge from modern physics. Einstein's relativity demonstrated that the concept of a universal now is an illusion. Two events that are simultaneous for one observer will not be simultaneous for another moving at a different speed. There is no privileged present moment that sweeps across the entire cosmos, which means presentism struggles to define what the present even is on a cosmic scale. If only the present is real, whose present are we talking about? A compromise between these two extremes is the growing block theory. This view proposes that the past and present are real, but the future is not. The universe is a four-dimensional block that is continually growing like a cosmic glacier, as each new moment solidifies into existence and is added to the ever-lengthening past. In this model, the past is fixed and unchangeable, a permanent part of reality, while the future remains an open realm of pure potential. The growing block theory offers an elegant solution to the problem of time's flow. There is a genuine objective becoming, as new slices of reality are constantly added to the block. You can point to the leading edge of the block and say, this is the present, this is where reality is actively being written. It preserves the reality of the past, allowing us to say that Julius Caesar truly exists in the same way we do, just at a different temporal location. He is not a ghost, but a real person frozen in the earlier parts of the block. However, this theory creates a strange metaphysical situation. If the past is real, then every moment of your childhood is just as real as the moment you are experiencing right now. Your 5-year-old self is out there in the block, laughing or crying. This raises profound questions about personal identity. Are you the same person as that child, or are you merely a later temporal part of a long, worm-like entity that stretches from your birth to your death? Your consciousness seems to be tied only to the present slice, unaware of the other slices of yourself that eternally exist in the past. Each of these theories of time carries dramatic implications for the nature of our existence. Presentism makes our lives an urgent, fleeting dance in a single spotlight. The growing block turns our lives into a finished sculpture that is still being carved with the final form unknown. The block universe sees your entire life as a timeless work of art, already complete. Your choices feel free because you are experiencing the story in sequence, but the entire narrative from your first breath to your last is already an inseparable part of the cosmic canvas. The flow of time may be the most persistent and powerful illusion we will ever confront. But where does this mysterious collapse of the wave function actually happen? The Copenhagen interpretation, the original and most pragmatic approach to quantum mechanics, offers a stark answer. Developed by Niels Bohr and Werner Heisenberg in the 1920s, this framework draws a firm line between the quantum world and the classical world of our instruments. In this view, a particle does not have a definite position or momentum until the very moment it is measured. Before observation, it exists only as a blur of probabilities, a wave of potential described by the wave function. The act of measurement itself is what forces this cloud of possibility to collapse into a single, concrete fact. This is not seen as a physical process we can further dissect. It is a fundamental, irreducible boundary between the unobserved and the observed. Think of rolling a die inside a closed box. According to Copenhagen, until you lift the lid and look, the die is not showing any number at all. It is in a fuzzy superposition of all 6 possibilities. The moment you see it, the wave function collapses and a single, definite outcome is realized. This interpretation is ruthlessly practical, focusing only on the outcomes of experiments and refusing to speculate about what is really happening when we are not looking. It treats the wave function not as a physical wave, but as a mathematical tool that encapsulates our knowledge. This pragmatic approach has been spectacularly successful, forming the foundation for almost all of modern technology, from lasers to the transistors in your phone. Yet it carries a profound philosophical cost. It places conscious observation, or at least a classical measuring apparatus, at the very center of reality. The moon is not there when no one is looking, because to ask that question is to step outside the bounds of what the theory can describe. The Copenhagen interpretation does not solve the mystery of quantum reality. It simply draws a circle around it and says, this is where our understanding must stop. We are left with a universe that only becomes solid under our gaze, a cosmic stage that remains dark until the spotlight of measurement is switched on. String theory is not the only path to a grand unification of physics. A formidable competitor has emerged, one that takes a radically different approach to the problem of quantum gravity. Loop quantum gravity does not attempt to replace particles with vibrating strings. Instead, it asks a more fundamental question. What if space itself is not a smooth, continuous backdrop, but is woven from a fabric of tiny, discrete loops? This theory quantizes the very geometry of the cosmos. In the world of loop quantum gravity, space is not infinitely divisible. It is composed of a network of one-dimensional lines or loops intersecting to form a fabric known as a spin network. Picture a cosmic spiderweb, but one where the threads themselves are the fundamental units of reality. These threads are unimaginably small on the scale of the Planck length, a distance so tiny that a single atom is larger by comparison than our Sun is to the entire solar system. The nodes where these loops intersect represent the tiniest possible volumes of space, while the loops themselves define the areas between them. This network is not embedded in space, it is space. The entire universe is this evolving, dynamic web of relationships. Time in this framework is also granular, ticking forward in discrete, indivisible steps. This granular nature of space-time has a profound consequence, one that tackles one of the greatest failures of general relativity, the singularity. Inside a black hole and at the moment of the Big Bang, Einstein's equations break down, predicting points of infinite density where the laws of physics cease to apply. Loop quantum gravity resolves this by making such infinities impossible. Because space is quantized, you cannot compress matter and energy into an infinitely small point. It is like trying to pour more and more water into a glass that can only hold a finite number of molecules. Eventually, you simply cannot fit any more in. When matter reaches this maximum possible density, a tremendous repulsive force is generated. This leads to a breathtaking prediction for the origin of our cosmos. The Big Bang was not the beginning of everything, but rather a big bounce. A previous universe may have collapsed under its own gravity, but instead of crushing itself into a meaningless singularity, it reached this maximum density and rebounded, exploding outward into the universe we inhabit today. Our entire cosmic history could be one cycle in an endless, cyclic process of expansion and contraction. This elegant solution does not require the extra dimensions of string theory, working instead within the familiar 3 dimensions of space and 1 of time. It presents a universe that is not a void, but a dynamic, woven tapestry of relationships, where the very fabric of reality has a finite, granular structure. The smooth spacetime of our daily experience is an illusion, a vast average of this churning quantum geometric sea. But the endless cycle of the Big Bounce is not the only alternative to a single, definitive beginning. Another profound vision emerges from the heart of string theory, suggesting our entire cosmic history was sparked by a shattering collision. This is the ekpyrotic universe model, a theory that replaces the Big Bang with a breathtaking cosmic crash. The name itself comes from the Greek word for conflagration or great fire. In this framework, our three-dimensional universe is not all there is. It is a membrane, or a brain for short, existing within a higher dimensional space. Picture our cosmos as a single, immense slice of bread floating within a grand cosmic loaf. Now imagine another parallel brain, another slice of bread, hovering a microscopic distance away in an unseen dimension. The ekpyrotic model proposes that these two brains, drawn together by an invisible force, periodically move toward each other and collide. The energy of that colossal impact is what we perceive as the Big Bang. It was not an explosion from a single point, but a firestorm ignited across the entire surface of our brain, instantly filling it with the searing heat and radiation that would later coalesce into galaxies and stars. This collision did not create a singularity of infinite density. Instead, it was a well-defined event where the kinetic energy of the moving brains was converted into the matter and energy of our universe. This elegant scenario completely sidesteps the need for a cosmic beginning from nothing, proposing instead a cyclic model of the cosmos. After the collision, the brains bounce apart, and the universe we know begins its expansion and evolution. But the story does not end there. As they move apart, the force that drew them together again slowly pulls them back, setting the stage for another collision in the far, far future, another ekpyrotic conflagration that will rebirth the cosmos anew. This model offers a compelling alternative to cosmic inflation, one that naturally explains the large-scale smoothness of the universe. As the two brains move toward each other, they flatten and smooth each other out through their gravitational interaction, much like two sheets of wrinkled paper being pressed together become flat. This process creates the remarkably uniform conditions we see in the cosmic microwave background, without requiring a period of faster-than-light expansion. Perhaps most excitingly, the ekpyrotic model makes a unique prediction that could one day be tested. The collision of these giant brains would have sent powerful gravitational waves rippling through the fabric of spacetime. Unlike the primordial waves predicted by inflation, these ekpyrotic waves would have a distinct signature, a specific pattern imprinted on the cosmic microwave background. Our most sensitive telescopes are now searching for this very fingerprint in the ancient light of the cosmos. Finding it would not only revolutionize our understanding of the Big Bang, but it would provide the first direct evidence that we live in a universe of hidden dimensions, one of many membranes in a much grander, cyclic reality. What if the world you see is nothing more than a desktop interface, hiding a far stranger reality beneath its familiar icons? This is the startling claim of Donald Hoffman's theory of conscious realism, a vision that turns our understanding of existence inside out. Hoffman, a cognitive psychologist, argues that spacetime and every physical object within it are not fundamental truths. They are simply a user interface, a kind of evolutionary desktop that our brains have constructed to help us survive. Think of the icon for a document on your computer's screen. That little picture is not the file itself, which is a complex arrangement of bits and code. It is a simplified symbol that allows you to interact with the deeper reality of the computer without needing to understand its underlying programming. In the same way, a tiger is not fundamentally a massive, striped, physical object. That is just the simplified icon your consciousness uses to represent a lethal threat in a deeper, non-physical realm. Your perception of space, time, and objects is a brilliant evolutionary adaptation designed to hide the overwhelming complexity of what is truly real, allowing you to navigate the world effectively without being paralyzed by its true nature. So what is actually there behind the icons? Hoffman proposes that the fundamental reality is a vast network of interacting conscious agents. These are not necessarily human minds, but the most basic units of consciousness itself, interacting with each other in a realm that exists beyond space and time. In this view, your own consciousness is not a product of your brain. Your brain is part of the user interface, a symbol within the simulation that represents your location and actions within the network of conscious agents. This radical idea provides a powerful explanation for the central puzzle of quantum mechanics, the role of the observer. If physical objects are not fundamental, then it makes perfect sense that they only snap into a definite state when a conscious agent interacts with them. The observer effect is not a mysterious collapse, but simply an agent making a selection from a menu of possibilities within the interface. This framework dissolves the hard problem of consciousness effortlessly, because consciousness is not emerging from matter, it is the primary substance of reality. Matter is what consciousness does when it interacts with other consciousness through a simplified, symbolic interface. You are not a physical body that has somehow learned to think. You are a conscious agent, and the body you inhabit, the world you see, is the avatar you are using to navigate an infinitely more complex and profound reality. The solid ground beneath your feet feels real, but it is merely the icon your mind has selected to represent a stable platform for action. Hoffman's theory dares us to consider that we have been mistaking the map for the territory all along, and that the true nature of the cosmos is a dazzling symphony of mind. Could the universe itself be learning from its own past? This is the provocative heart of biologist Rupert Sheldrake's theory of morphic resonance, a vision where nature is guided not just by fixed laws, but by a kind of cumulative memory. Sheldrake challenges one of science's deepest assumptions, that the laws of nature are eternal and unchanging, written into the cosmos at the moment of the Big Bang. He proposes instead that they are more like habits, patterns that become increasingly ingrained through repetition. The mechanism for this cosmic habit formation is what he calls the morphic field, an invisible organizing principle that shapes everything from the form of a crystal to the instincts of a bird. Think of how you learn a new skill, like riding a bicycle. The first time is difficult and awkward, but with practice it becomes second nature. According to Sheldrake, this is not just a change in your brain, but a change in the very morphic field for bicycle riding. Your successful attempts add to a collective pool of information, making it slightly easier for the next person anywhere in the world to learn the same skill. The field resonates with the patterns of the past, influencing the present. This idea offers a radical explanation for some of biology's greatest puzzles. How do flocks of birds move with such perfect, instantaneous coordination, as if sharing a single mind? A morphic field for that species could be the unseen medium connecting them, a collective memory of flight paths and evasive maneuvers. Even the development of an embryo is a stunning feat of morphic resonance. A single fertilized cell contains the genetic blueprint, the instructions for building an organism, but how does it know exactly where to grow an eye or a limb? Sheldrake suggests it is tuning into the morphic field of its species, a resonant memory of countless ancestors that have taken the same developmental path before it. This theory extends beyond the living world into the heart of chemistry itself. When a new compound is first synthesized in a lab, it is often notoriously difficult to crystallize. Yet, once it has been crystallized somewhere in the world, other labs find the process becomes mysteriously easier. The conventional explanation is that microscopic seed crystals are carried on the clothing of scientists or through the air. Sheldrake offers a different possibility. The first successful crystallization establishes a new morphic resonance, a pattern that makes it easier for the same crystal structure to form anywhere else. The laws of chemistry have not changed, but their expression has become more habitual. This is a universe that is not static, but a living, learning system, where every action and every form contributes to a growing library of influence, shaping the future through the resonant echo of all that has come before. The universe may not have required a miracle to come into being. It might simply be the ultimate free lunch. This is the startling promise of the zero-energy universe hypothesis, a theory that calculates the total energy of the cosmos and arrives at a profound answer: zero. How can a universe teeming with galaxies, stars, and life possibly amount to nothing? The secret lies in a cosmic balancing act of breathtaking precision. All the positive energy contained within matter, from the mass of your body to the furious power of a quasar, is perfectly counterbalanced by a vast reservoir of negative energy, the gravitational potential energy of the entire cosmos. Gravity, the force that pulls things together, acts like a cosmic debt. Every object attracts every other object, and the energy required to pull them apart to overcome this gravitational binding is considered negative. Think of a ball resting at the bottom of a deep well. To lift the ball out of the well and set it free, you must add a significant amount of positive energy. From the perspective of the ball at the bottom, its gravitational potential energy is a large negative number. Now imagine that well is the entire universe. The sum of all the positive mass energy and all this negative gravitational energy cancels out to precisely zero. Our magnificent cosmos in its entirety may have a net energy of nothing at all. This elegant idea suggests a mind-bending possibility that the universe could have spontaneously emerged from a vacuum fluctuation, a temporary bubble of nothingness, without violating the sacred law of energy conservation. If the total energy was always zero, then no energy needed to be created or destroyed at the moment of Genesis. The Big Bang was not an explosion of energy into empty space, but a sudden, spontaneous localization of zero energy into the positive and negative components we see today. You are not made from something that was added to the void. You are a fluctuation in a perfect equilibrium, a ripple in a zero-energy field. Your existence in this view is a testament to the fact that the most profound something can be built upon the most absolute nothing. If life is the ultimate free lunch, perhaps it is also the master chef. Robert Lanza's biocentric universe theory proposes a truly revolutionary shift, placing biology and consciousness at the very center of existence. In this view, life is not a fragile accident in a vast, indifferent cosmos. Instead, the universe is fundamentally biocentric, meaning life creates the universe, not the other way around. Lanza argues that space and time are not the hard, external containers we perceive them to be. They are not the stage upon which life stumbles. They are instead tools of the mind, constructs of our animal senses that help us navigate a reality that is, at its core, relative to the observer. We have been tricked by our own perception into believing in an objective, external world of stars and galaxies existing independently of us. Biocentrism suggests the opposite. The stars and galaxies only snap into a definite state through the act of perception by a conscious being. This offers a powerful biological solution to the persistent puzzles of quantum mechanics. The famous double-slit experiment, where a particle's behavior changes depending on whether it is observed, is not a quirk of tiny particles. It is a fundamental feature of reality that only makes sense when you realize the observer is essential. Without a living creature to perceive it, the universe exists only as a haze of undefined potential. The tree falling in the forest with no one around truly makes no sound, because sound is an interpretation of air vibrations by a biological auditory system. More than that, it has no definite form at all until a conscious organism interacts with it. This perspective also tackles the mystery of the universe's fine-tuning, the fact that the physical constants seem perfectly calibrated to allow for life. The answer for biocentrism is simple. A universe that was not tuned for life would never be observed. We do not find ourselves in a life-friendly universe by incredible luck. We find ourselves in a life-friendly universe because the very act of our existence requires it. The laws of physics are not a set of pre-written rules. They are the outcome of our consciousness. Your reality is a deeply personal biological phenomenon, a universe brought into being by the very life that inhabits it. David Bohm offered a radical vision to heal the quantum rift, suggesting our fractured world of separate objects is an illusion. He proposed that reality possesses two fundamental orders. The explicate order is the world we perceive, where things are unfolded and manifest with distinct locations in space and time. This is the realm of tables, trees, and distant stars. But beneath this surface lies what Bohm called the implicate order, a deeper, enfolded reality where everything is seamlessly interconnected and whole. In this hidden dimension, the entire universe is woven into a single, unbroken fabric. Think of a drop of ink spiraling into a viscous fluid. As you stir, the ink seems to disappear, becoming enfolded into the liquid. This is the implicate order. If you then stir in reverse, the drop of ink miraculously reappears, becoming explicate once more. Every part of the fluid contains information about the whole, perfectly enfolded within it. Bohm argued that the entire cosmos operates this way. Every particle, every person, every galaxy is an unfolded expression of this deeper, implicate whole. The apparent separateness we see is just a temporary, explicate phenomenon. This framework elegantly explains the strangeness of quantum entanglement, where two particles remain connected across vast distances. In Bohm's view, they are not communicating faster than light. Their connection is not transmitted, it is revealed. Both particles are simply manifestations of the same underlying implicate reality, so their correlation is immediate and inherent. Guiding this unfolding process is what Bohm termed the quantum potential, a subtle information field that pilots particles along their paths. This is not a force in the traditional sense, but more like a cosmic map of the whole, influencing each part from within the implicate order. Your own consciousness, in this view, is not locked inside your skull. It is an active participant in this unfolding, a localized expression of the same fundamental wholeness that underlies all of existence. You are not an isolated observer in a dead universe, but a unique ripple on the surface of an infinite, living ocean. Perhaps the most intimate stage for these quantum dramas is inside your own head. A theory known as orchestrated objective reduction, or OR, proposes that consciousness is not a classical computation of the brain, but a profound quantum process happening within the neurons themselves. Developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, this controversial idea locates the seat of consciousness in structures called microtubules. These are tiny, cylindrical scaffolds made of protein, found in nearly every cell, including the neurons of your brain. For decades, neuroscience has focused on neurons as simple on-off switches, but OR suggests the real magic happens inside them, within these intricate molecular networks. Penrose started from a deep philosophical problem. He argued that human understanding, things like mathematical insight or the grasping of beauty, possesses a non-computable quality. This means no standard computer algorithm, no matter how complex, could ever replicate it. He believed this required a process rooted in the non-algorithmic, unpredictable world of quantum gravity. Hameroff provided the biological counterpart, suggesting that microtubules are perfectly structured to support delicate quantum states. Their orderly, lattice-like architecture could protect quantum superpositions, where a particle exists in multiple states at once, from the disruptive noise of the warm, wet brain. In this theory, your consciousness arises from these quantum computations. Each microtubule acts like a quantum computer, and the neurons orchestrate their activities, hence the name orchestrated objective reduction. The reduction is the key moment, the collapse of the quantum wave function. But this is not a collapse caused by a mysterious observation. Penrose proposed it is an objective event, a spontaneous collapse driven by the curvature of spacetime itself, when the superposition states become too gravitationally unstable to persist. This moment of objective reduction is when a conscious moment flashes into existence. It is the ticking clock of your subjective experience, with each reduction yielding a new precept, a new moment of awareness. This process could elegantly explain the unity of consciousness, the famous binding problem. How do the myriad signals from your eyes, ears, and touch combine into a single, seamless experience of looking at a sunset? If quantum entanglement links the microtubules across vast networks of neurons, then information could be processed in a unified, holistic way, creating that singular sense of self. Your feeling of free will, that uncanny ability to make a genuine choice, might then stem from this non-algorithmic quantum decision point, a creative moment where the universe itself settles on one possibility. The theory remains fiercely debated, with many physicists skeptical that such delicate quantum states could survive in the noisy environment of the brain. Yet it stands as a bold attempt to bridge the deepest chasm in science, connecting the weirdness of the quantum world directly to the intimate miracle of your own mind. The smooth, one-way flow of time seems so fundamental to our existence, yet the equations of quantum mechanics remain stubbornly indifferent to its direction. A radical family of theories takes this indifference seriously, proposing a universe where quantum events are perfectly symmetric in time. This is the world of time-symmetric quantum mechanics, where the future can reach back and shape the past just as the past pushes forward into the future. One such framework is the two-state vector formulation. It suggests that to fully understand a quantum system at any given moment, you must know two things, not one. You need the usual wave function evolving from the past, but you also need a second wave function evolving backward from a future measurement. The present reality is a handshake between these two waves, one from yesterday and one from tomorrow. Imagine a detective trying to understand a single moment in a crime. They would look at the evidence leading up to it, the clues from the past, but they would also look at the evidence that came after, the consequences in the future. Only by combining both perspectives can they understand what truly happened in that instant. In this quantum view, a particle's path is not set solely by its initial conditions. It is also guided by its final destination, a phenomenon known as retrocausality. This does not mean you can change the past in a dramatic grandfather paradox way. Instead, it means that the past itself was always flexible, a set of possibilities that were only finalized when a future event locked them into place. Think of a sculptor looking at a block of marble. The final statue they intend to create influences every single chip of the chisel from the very beginning. The future form is, in a real sense, guiding the creation of the past. Retrocausal models challenge causality at its core, suggesting that cause and effect can be a two-way street. An experiment performed today could be the reason a particle behaved in a specific way a million years ago. This is not magic, but a fundamental property of a timeless quantum reality. The delayed choice experiments we encountered earlier fit perfectly here. Our decision to measure a photon today settles what path it took billions of years in the past. In a time-symmetric universe, this is not a bizarre exception. It is the norm. The arrow of time we experience so powerfully may be a large-scale illusion, a thermodynamic tendency toward disorder that emerges from a deeper, more symmetrical layer of physics where every moment is eternally connected to every other. We are left with a cosmos where the flow of time is not a river, but a vast, interconnected web, and our conscious journey from past to future is just one thread in an infinitely more complex tapestry. This cosmic hologram might hold the key to our universe's ultimate fate. The holographic dark energy model takes the principle that reality is a projection, and applies it to the greatest mystery in modern cosmology, the accelerating expansion of the universe. We see galaxies flying apart faster and faster, driven by a mysterious repulsive force we call dark energy. But what is it? The leading candidate is the cosmological constant, a fixed energy density woven into the fabric of space itself. This idea, however, comes with a devastating problem. When physicists try to calculate the value of this energy from quantum theory, they get a number that is 120 orders of magnitude too large. That is a 1 followed by 120 zeros. A universe with that much energy would have been torn apart in a fraction of a second after the Big Bang. Our universe clearly has a much smaller amount of dark energy, and we have no idea why. The holographic dark energy model offers a breathtakingly elegant solution. It suggests that dark energy is not a property of empty space, but a consequence of the information bounds of our cosmic hologram. Remember, the holographic principle states that the information content of a region is proportional to its surface area, not its volume. Now apply that to the entire observable universe. Our cosmic horizon, the farthest distance we can possibly see, acts like the two-dimensional surface storing the information for our three-dimensional world. The model proposes that the amount of dark energy in the universe cannot be arbitrary. It is limited by the maximum amount of information that can be stored on that cosmic horizon. The energy density of the vacuum is not a random constant, but a dynamic quantity that evolves as the universe expands and the area of the horizon grows. Think of it like a computer hard drive. The data you can store is limited by the drive's capacity. In the same way, the total energy in our cosmic volume is limited by the information capacity of its bounding surface. This naturally leads to a very small value for dark energy, one that aligns surprisingly well with our astronomical observations. It solves the cosmological constant problem by linking the largest scales of the cosmos directly to the fundamental limits of information from the quantum world. The acceleration of the universe is not a mysterious force, but a natural outcome of the holographic nature of reality. We are not just living in a hologram, we are living in a hologram that is dynamically encoding itself, and the dark energy we measure is a direct readout of that cosmic data storage process. But if the universe is a computer, what kind of processor does it use? The idea of a computational cosmos forces us to ask whether it runs on classical or quantum principles. A classical universe computer would operate like a vast network of deterministic switches, processing information in a step-by-step predictable manner. Yet our reality is filled with genuine randomness and probability, hallmarks of the quantum world. This suggests the cosmic computer is likely quantum at its core, processing a near-infinite number of possibilities in parallel before settling on a single, definite outcome. Such a quantum computer would not be calculating in a way we can easily imagine. It would be performing a cosmic computation of unimaginable complexity, where every particle interaction represents a logical operation and every field fluctuation is a step in the program. The physical laws we have discovered, from the elegant simplicity of general relativity to the probabilistic rules of quantum mechanics, might be the high-level software language of this system, the user-friendly interface for a process operating at a far deeper level. This raises a profound question about the purpose of it all. Is the universe computing something specific, perhaps optimizing for the creation of complexity or the maximum diversity of structures? Could black holes be the ultimate data processors, efficiently erasing information to free up cosmic memory, or are they portals to other computational domains? The very fact that we can uncover mathematical laws suggests the universe is at least computationally tractable, that its operations can be understood, even if the ultimate goal of the computation remains a magnificent, unsolved mystery. Perhaps reality is not something we discover, but something we actively build with every thought and glance. This brings us to a philosophy that turns the entire quest inward, focusing not on what is out there, but on the very act of experiencing it. Edmund Husserl's phenomenological approach proposes a radical shift in perspective. He argued that to understand reality, we must first suspend our natural assumption that an external world exists independently of us, a process he called bracketing or the epiché. Instead of asking if a chair is real, phenomenology asks, what is the structure of the experience of that chair? How does its brown color, its solid shape, its inviting presence appear in our consciousness? This method meticulously examines the contents of experience, from the sound of rain to the memory of a friend's smile, without making any claims about their ultimate origin. Husserl called this the study of phenomena, the things as they appear to us. At the heart of this approach is the concept of intentionality, the idea that consciousness is always consciousness of something. Your mind is not a blank slate. It is a dynamic beam of attention, forever reaching out and giving meaning to the world. You do not just see colored shapes, you see a threatening storm cloud. You do not just hear vibrations, you hear a comforting voice. Reality, in this view, is constituted through these intentional acts. The tree outside your window gains its meaning as a tree, its identity as a source of shade or a home for birds through your conscious engagement with it. This philosophy deeply influenced later thinkers who took this idea even further, suggesting that the solid, objective world we take for granted is in fact a collaborative construction of countless conscious minds, each contributing to a shared reality through their intentional focus. The world is not simply presented to us, we are constantly and silently co-creating it through the very structure of our awareness. Our stubborn habit of seeing the world as a collection of solid, separate objects might be the greatest illusion of all. Alfred North Whitehead offered a radical alternative, a vision where reality is not built from things but from happenings. This is process philosophy, a metaphysics that declares the fundamental units of the cosmos are not enduring substances like electrons or atoms, but fleeting events which Whitehead called actual occasions. Each occasion is a drop of experience, a momentary pulse of existence that gathers up the entire universe and adds its own unique, creative response before perishing, giving way to the next pulse. Think of reality not as a noun but as a verb, a constant, flowing becoming. A rock is not a static object. It is a slow, immensely patient society of these occasions, a harmony of processes vibrating at a glacial rhythm. Your own stream of consciousness is a rapid-fire chain of these actual occasions, each moment of experience inheriting the one before and reaching toward the next. The entire cosmos is a living, growing network of these creative events. At the heart of this process is what Whitehead termed prehension. Every actual occasion does not exist in isolation. It feels or prehends its entire past. It takes in the whole of the universe that has led up to it, not through conscious thought, but through a physical feeling of everything that has come before. Your experience of this very moment prehends the light from your screen, the sound of these words, the memory of what you just heard, and the gravitational pull of the entire galaxy. Every event is a response to the entire cosmic history that has culminated in its birth, but this is not a deterministic chain. The true magic of an actual occasion is its creative advance. After prehending the entire past, it does not just mechanically churn out a predetermined future. It possesses a spark of self-causation, a moment of genuine novelty where it decides how it will respond to all that it has felt. This is where freedom and novelty enter the universe, not as random accidents, but as the very engine of cosmic evolution. The universe is not a pre-recorded movie. It is an improvisational jazz performance where each musician, each actual occasion, listens intently to the entire band and then adds their own unique, spontaneous riff that changes the course of the music forever. This dynamic view elegantly bridges the chasm between mind and matter. In Whitehead's universe, there is no hard problem of consciousness because experience is fundamental. Even the most basic actual occasion has a minute proto-mental aspect, a subjective aim toward its own satisfaction. The deep, rich consciousness you experience is not a sudden emergence from dead matter. It is the culmination of a spectrum of experience that runs all the way down to the roots of reality. Process philosophy presents a cosmos that is alive, relational, and creative at its very core. A universe that feels its own past and constantly, creatively, dreams its future into being. The laws of physics we take for granted may not be the deepest level of reality. A radical new framework called constructor theory, pioneered by physicist Chiara Marletto, proposes a profound shift in perspective. Instead of describing the universe in terms of what happens, it describes reality in terms of what can and cannot happen. It asks not about the trajectory of a ball thrown in the air, but about the fundamental principle that makes throwing a ball possible at all. The theory identifies two core categories: possible transformations and impossible transformations. A possible transformation is any change that can be brought about by a constructor, a physical system that can cause that change and remain unchanged itself, ready to do it again. Your oven is a constructor for transforming raw dough into bread. Your brain is a constructor for transforming sensory data into conscious thought. An impossible transformation is one that no constructor can ever perform, like building a perpetual motion machine that creates energy from nothing. This simple, powerful distinction provides a new language for physics. It treats information not as a ghostly abstraction, but as a concrete, physical property. In constructor theory, a piece of information is defined as any attribute that can be copied. This immediately unites the worlds of quantum mechanics and information science, because the possibility or impossibility of copying a certain state is a fundamental property of reality. The theory also elegantly tackles the arrow of time. The reason you can turn an egg into an omelette but never an omelette back into a whole egg is not a law of initial conditions, but a fundamental principle of impossibility. Constructor theory states that transforming a disordered state into an ordered one, like unscrambling an egg, is an impossible transformation. This is a statement about the nature of reality itself, not just a statistical tendency. By focusing on these enduring principles of possibility, constructor theory aims to sit beneath all our current theories, from quantum mechanics to general relativity, providing a single, unified foundation. It suggests that the universe is not a collection of particles and forces, but a vast, interlocking set of possible and impossible tasks, a cosmic rulebook written in the language of transformation, waiting to be read. Causal set theory presents a universe of breathtaking simplicity at its foundation, built not from a smooth fabric but from a vast collection of discrete events. Imagine reality as an immense growing heap of sand, where each grain represents a single, fundamental moment in the history of the cosmos. These grains are not scattered randomly. They are connected in a very specific way by the unbreakable chain of cause and effect. One grain, one event, can only influence another if there is a causal link between them, a cosmic line drawn from cause to effect. In this view, the smooth, four-dimensional spacetime of Einstein's theories is not primary. It is a secondary, emergent illusion, a blurry, large-scale approximation that arises from the immense number of these causal connections, much like a smooth, continuous image emerges from the countless tiny dots of a newspaper photograph. The theory brilliantly sidesteps the problem of infinite densities that plague our current understanding of black holes and the Big Bang. In a continuous space-time, you can theoretically compress an infinite amount of energy into an infinitely small point, a singularity where the laws of physics break down. But in a causal set, this is impossible. There is a fundamental limit to how many of these discrete grains, these fundamental events, can be packed into a given region. You cannot have an infinite number of grains because the set is discrete by its very nature. This means the universe has a built-in resolution, a pixelated core that prevents the nonsensical infinities of singularities from ever forming. The Big Bang was not an explosion from an infinitely dense point, but the rapid unfolding of a new, vibrant causal structure. A black hole's heart is not an infinitely small pit, but a region where the causal connections become so dense and complex that our classical notions of space and time cease to have meaning. This granular nature of reality also offers a profound explanation for the arrow of time. The causal set itself is always growing, always adding new grains. This relentless growth, this irreversible process of new events being born from the causes of the past, may be the true source of time's one-way direction. We are not moving through time, we are witnessing the universe constantly constructing itself, one causal connection at a time, building the solid stage of space-time from the fundamental relationships between events. But if space-time is woven from a causal set of discrete events, what is the loom on which it is woven? The emergent space-time hypothesis proposes that space and time are not the fundamental stage of reality, but are themselves collective illusions emerging from a deeper, more primitive layer of quantum information. This radical idea suggests that the smooth, continuous space-time of Einstein's general relativity is like the surface of a lake, a large-scale phenomenon that hides a turbulent, churning reality beneath. At the tiniest possible scale, the Planck scale, the concepts of here and now break down entirely. In their place is a frothing sea of quantum relationships, a network of entangled connections from which the familiar dimensions of space and time condense, much like the temperature of a gas emerges from the frantic, chaotic motion of countless individual molecules. The conflict between quantum mechanics and general relativity, the century-long struggle to unite the very small with the very large, may simply vanish once we realize that gravity and space-time are not fundamental. They are secondary, emergent properties of an underlying quantum reality. This is not just a philosophical shift, it is a potential revolution in physics. Think of a three-dimensional image emerging from a flat, two-dimensional hologram. The depth and volume you perceive are not inherent to the image itself, they are generated by the complex interference of light waves. In the same way, our four-dimensional spacetime continuum could be a holographic projection from a boundary layer of quantum bits that exists at the edge of the universe. The force of gravity would then not be a fundamental force, but a kind of entropic force, an emergent effect of the system's tendency toward disorder, similar to how the pressure in a gas emerges from the random collisions of atoms. When you stand on the ground, you are not being pulled down by a mysterious force. You are being pushed by the statistical tendency of the quantum information describing you and the Earth to maximize its entanglement. This perspective elegantly reinterprets the fabric of the cosmos, transforming it from a static backdrop into a dynamic, collective behavior of more basic building blocks. The smooth geometry of spacetime is a macroscopic average, a grand illusion that becomes real only when we zoom out from the frantic quantum dance at the foundation of everything. This idea of a multiverse of all possible stories finds its most radical champion in the philosopher David Lewis. He proposed a theory of staggering boldness called modal realism, arguing that every single possible world is just as real and concrete as our own. Every world you can imagine and every world you cannot exists in a vast and disconnected pluriverse. Our cosmos is not special. It is merely one neighborhood in an infinite metropolis of realities. Lewis was not talking about distant planets or parallel dimensions within our own spacetime. He meant entirely separate cosmic systems, each with its own complete history, its own laws of physics, and its own versions of you. There is a world where the dinosaurs never went extinct and intelligent reptiles now gaze at their moons. There is a world where you took a different route to work this morning and had a conversation that changed your life. In Lewis's view, these are not mere fantasies or hypotheticals. They are actual physical places, every bit as real as the room you are sitting in now. The only thing that makes our world actual to us is that we are in it. For the lizard philosopher in that other cosmos, his world is the actual one, and ours is just a distant possibility. This is a pluriverse of absolute abundance, where no possibility is ever wasted, and every story is being told. But how can all these worlds be real if we cannot see them or travel to them? Lewis argued they are causally and spatiotemporally isolated from one another. They are not far away in our space, they are entirely separate, with no bridges or wormholes connecting them. You cannot visit these worlds, but you can talk about them, and for Lewis, that is the key. We use the concept of possibility every day. We say it is possible that it will rain tomorrow, or that you might have been an artist instead of what you are. Modal realism takes these statements literally. When we say it is possible for you to have been an artist, we are referring to a genuine, concrete world out there in the pluriverse where a counterpart of you, shaped by a slightly different chain of causes, is indeed painting for a living. This counterpart is not you in the strict sense, but a person who resembles you closely in important ways, born from the same origins but living a different life. This framework provides a powerful and elegant solution to age-old philosophical puzzles about necessity and possibility. What does it mean to say water is necessarily H2O? It means that in every possible world where that substance exists, it has that chemical structure. The laws of logic are not just rules we follow, they are descriptions of the structure of the entire pluriverse. Yet the cost of this elegant solution is a breathtaking ontological extravagance. Lewis asks us to accept the real, physical existence of a world where unicorns graze on purple grass, a world where gravity pushes instead of pulls, and a world where a version of you is the emperor of a galactic empire. The theory demands we take all of these as facts. The weight of this infinite reality can feel overwhelming, challenging our deepest intuitions about what is real and what is mere imagination. It suggests that our choices are not about creating a single future, but about selecting which path, already fully realized in the pluriverse, we will consciously experience. Your life is not a thread being spun, but a single, already woven thread in an infinite tapestry of all that could ever be. This philosophical stalemate between mind and matter might have a surprising resolution. A third path, known as neutral monism, cuts directly through the heart of the debate. It proposes that both consciousness and the physical world are not the ultimate foundations of reality. Instead, they are two different aspects or manifestations of a single, underlying neutral substance. The roots of this elegant idea reach back to the 17th century and the brilliant, persecuted philosopher Baruch Spinoza. He argued that there is only one infinite substance, which he called God or nature. This single substance possesses an infinite number of attributes, but we finite humans can only perceive two of them, thought and extension. In Spinoza's system, your mind is not a ghost in a machine. Your mind is the idea of your body, and your body is the object of that idea. They are one and the same thing, seen from two completely different points of view, like the inside and outside of a single sphere. Centuries later, the pioneering psychologist William James arrived at a similar conclusion from his studies of human experience. He found that the raw data of consciousness, what he called pure experience, does not initially come labeled as mental or physical. It is just a seamless, flowing stream. A moment of pain, for instance, is not first a subjective feeling that then gets projected onto a physical body. It is a single, neutral event that can be taken in two ways. From the inside, it is a painful sensation. From the outside, observed by a doctor, it is the firing of specific nerve cells. The experience itself is prior to the categories we use to split it apart. Modern philosophers have revived this framework to tackle the seemingly insurmountable mind-body problem. The central puzzle is how something as intangible as a thought can possibly interact with something as solid as a brain. If you are a materialist, you must explain how mind emerges from meat. If you are an idealist, you must explain why the world of mind appears to have such stubborn, objective physical laws. Neutral monism dissolves this problem entirely. It suggests that both mind and matter emerge from a common source that is, in itself, neither mental nor physical. We do not yet know the nature of this neutral substrate. Perhaps it is a field of pure information, or a realm of proto-properties that only become mental or physical through the specific relationships they form. Think of the same data on a computer drive. When processed by a graphics card, it manifests as a visual image, a shape and colors you can see. When processed by a sound card, that very same data manifests as a symphony, a rich auditory experience. The data itself is neutral. It is not an image or a sound. It only becomes one or the other through the mode of interaction. In the same way, the neutral substrate of reality might express itself as a physical brain state when observed from the outside, and as a conscious thought when experienced from the inside. They are not causing each other, they are parallel expressions of a deeper, unified reality. This perspective reframes our entire existence. You are not a mind and a body struggling to communicate. You are a unified entity whose inner life and outer form are two sides of the same profound coin, forever flipped in the act of being. Our stubborn sense of a single, objective reality might be a magnificent consensus illusion. Panpsychism's theory of quantum Darwinism proposes that the solid, classical world we all agree upon emerges from a process strikingly similar to natural selection, but playing out in the quantum realm. The puzzle it solves is profound. Why do we all see the same chair in the same location, when quantum mechanics insists that before observation, that chair exists in a blurry superposition of many possible states? The answer lies not in a mysterious collapse, but in a ruthless competition for survival in a sea of information. In the quantum world, every object is constantly interacting with its environment. A single particle is bombarded by photons of light, buffeted by air molecules, and entangled with countless other particles. This relentless interaction is like a constant, brutal interrogation. Most quantum states are fragile and delicate. When probed by the environment, they quickly decohere, losing their quantum weirdness and fading away. But a few special states are robust. They are the evolutionary winners. These are the pointer states, states that can withstand the environmental onslaught without being drastically altered. A particle's definite position, for instance, is a pointer state. When a photon bounces off a particle in a specific location, that location is copied onto the photon. That photon then travels away, carrying the information with it, and then another photon does the same, and then a billion more. This is the Darwinian part. The information about the pointer state is replicated and broadcast into the environment with staggering redundancy. Think of a secret whispered in a crowded room. A fragile, complex secret might be misheard and lost, but a simple, clear secret like the time of day gets repeated from person to person until nearly everyone in the room knows it. That is the objective reality you perceive. The chair is there because its location and shape have been copied onto trillions of photons bouncing off it, each photon carrying the same message to any potential observer. You do not see the chair's underlying quantum nature for the same reason you do not see the individual atoms in the air. You only see the consensus, the information that has been so widely replicated that it becomes impossible to ignore. Your consciousness is not causing the collapse of the wave function. It is simply tapping into this pre-existing, publicly available stream of classical information. The world you see is the one that was fit enough to survive and reproduce its information across the environment, a shared reality forged by the relentless process of quantum natural selection. The very geometry of space-time may be a beautiful but ultimately superficial layer. A revolutionary approach to particle physics bypasses our conventional notions of location and cause entirely, suggesting that the most fundamental layer of reality is a purely mathematical shape. This is the amplituhedron formulation pioneered by physicist Nima Arkani-Hamed. It proposes that the complex calculations predicting how subatomic particles scatter and interact, which traditionally require thousands of pages of intricate mathematics, can be replaced by a single, elegant geometric object, the amplituhedron. This jewel-like structure exists in an abstract, higher-dimensional space, and its volume directly encodes the probabilities of different particle collision outcomes. The profound implication is that our cherished assumptions of locality and unitarity, the bedrock of modern physics, might not be fundamental at all. Locality is the idea that particles interact only when they are at the same point in space. Unitarity is the rule that probabilities for all possible outcomes must always add up to 100%, ensuring the conservation of information. These principles have always been manually stitched into our equations, yet the amplituhedron, simply by existing as a geometric form, automatically spits out answers that respect these rules without having them built in from the start. It is as if the shape itself knows the rules of the game, not because it was programmed with them, but because they are natural consequences of its deeper geometry. Imagine you are trying to understand the concept of a shadow. You could meticulously measure the angles of light and the shape of the object casting it. The amplituhedron suggests a different path. Instead of analyzing the shadow, you simply contemplate the perfect, three-dimensional object that creates it. Our spacetime, with its local interactions and definite causes, might be the shadow. The amplituhedron is the object. This geometric approach completely sidesteps the thorny issue of quantum gravity's infinities that plague other theories, offering a startlingly clean and finite way to compute the behavior of reality at its most fundamental level. The solid stage of space and time, and the rules that seem to govern it, may be emergent phenomena, secondary effects that bubble up from a far more pristine and profound mathematical reality. The universe might be playing the world's most complex game of life. This is the cellular automaton universe theory, a specific and mesmerizing vision of digital physics. Imagine a vast, infinite grid, a cosmic chessboard where each square is a cell that can be in one of two states, on or off, alive or dead. Now imagine a set of simple rules governing the fate of every cell. The most famous example is Conway's game of life, where a cell's state in the next moment depends solely on the states of its 8 immediate neighbors. If a live cell has too few neighbors, it dies of loneliness. If it has too many, it dies of overcrowding. If a dead cell has exactly the right number of live neighbors, it springs to life. From these 3 simple rules, an astonishing universe of behavior unfolds. Gliders, small patterns that drift diagonally across the grid, emerge like elementary particles. Still life's stable configurations appear like simple atoms. Complex, self-replicating patterns can arise, acting like primitive forms of life. The entire cosmos, in this view, could be the result of a similarly simple algorithm ticking forward in discrete steps. The flowing river, the swirling galaxy, and the thought in your mind are not made of a continuous substance. They are immense, stable patterns propagating across this fundamental grid, their complexity emerging from the relentless application of trivial rules. This transforms our understanding of physical laws. The law of gravity or the rules of quantum mechanics would not be fundamental truths written into the cosmos. They would be emergent phenomena, the large-scale consequences of the underlying computational process, just as the laws of thermodynamics emerge from the collective motion of atoms. We are not living in a universe of forces and fields, but in a cosmic computation whose output is reality itself, a breathtaking tapestry woven from the simplest possible threads. There is a perspective that dissolves the finality of death entirely, proposing that your conscious self is not a temporary guest in the cosmos but a permanent feature of it. The eternal consciousness theory argues that consciousness is the one fundamental, unchanging reality of the universe, and that our individual minds are merely waves rising and falling on its infinite ocean. This is not about reincarnation in the traditional sense of a soul migrating from body to body. It is the more profound claim that the universal consciousness is the only true self, and what you experience as your personal identity is a temporary, localized expression of that single, eternal awareness. Your birth was not the beginning of you, and your death will not be your end. They are simply transitions, moments when the universal consciousness focuses through and then withdraws from the particular lens of your body and brain. Your deepest sense of being, the pure I am that exists before any thought or memory, is not generated by your brain. It is the foundational substance of existence itself, momentarily experiencing the world through your unique perspective. This radically redefines our understanding of life and death. If this theory is true, then death is not an annihilation but a release, a letting go of a temporary story and a return to the undifferentiated whole. The fear of oblivion loses its grip because the core of what you are cannot be extinguished. It is like a wave realizing it is not a separate entity, but an inseparable part of the entire ocean. The wave's form is temporary, but the water itself is eternal. This view finds powerful resonance in ancient spiritual traditions, particularly Advaita Vedanta, which teaches that the individual soul and the universal consciousness are one and the same, and that the perception of separation is the primary illusion of existence. It also aligns with the insights of mystics across cultures who speak of a direct, unmediated experience of union with the divine or the absolute, a state where the sense of a separate self completely vanishes, leaving only pure, boundless awareness. What then becomes of your personal identity, your cherished memories, your loves and your losses? From this perspective, they are not erased, but they are relativized. They are the beautiful, intricate content of one particular dream dreamed by the eternal consciousness. They are real within the dream, just as the events of a novel are real within its pages, but they are not the ultimate reality of the dreamer. You are not the character in the story, you are the author who has temporarily and completely become the character. This transforms the search for meaning from a personal quest for immortality into a journey of recognition, a remembering of our true nature. The purpose of life is not to desperately cling to a temporary self, but to awaken to the eternal self that we have always been, and in doing so, to see the same eternal self in everyone and everything we encounter. Our own minds might be a perfect example of a holographic reality in action. The holographic brain theory, developed by neuroscientist Karl Pribram, proposes that your brain itself functions like a hologram. This idea emerged from a puzzling mystery in neuroscience. For decades, researchers tried to map memories to specific locations in the brain, but the results were baffling. No matter which small section of a rat's brain they removed, the memory of a complex maze could not be entirely erased. It was as if the memory was stored everywhere at once, and any piece of the brain could access the whole. Pribram realized this was eerily similar to how a hologram works. If you shatter a piece of holographic film, any single fragment can still reconstruct the entire three-dimensional image, though with less clarity. The image is not stored in one spot, it is distributed across the entire surface, with each part containing information about the whole. Pribram suggested the brain does the same with memory and perception. Instead of having a dedicated filing cabinet for your grandmother's face or the smell of rain, your brain stores these memories as intricate interference patterns spread across the vast network of neurons. When you recall your grandmother, your brain does not retrieve a single file. It illuminates the entire holographic plate, reconstructing the memory from the distributed pattern. This elegantly explains the brain's immense storage capacity, as a hologram can hold a staggering amount of information in a very small space. But the theory goes even further, potentially explaining the very nature of conscious experience. The world you perceive, with its rich textures and vivid depth, may not be a direct readout of sensory data. Your brain could be interpreting frequencies from a deeper, holographic realm, translating them into the solid, three-dimensional reality you navigate every day. You are not just looking at a holographic universe, you are a walking, talking holographic projector constantly creating the world you call real. The quantum world may not be confined to physics labs. It might be humming inside your mind at this very moment. While OR places consciousness in the delicate quantum vibrations of microtubules, it is not the only theory that sees the brain as a quantum device. A broader quantum mind hypothesis suggests that various quantum phenomena play crucial roles in our neural circuitry, potentially solving some of the deepest mysteries of thought and awareness. One key concept is quantum coherence, the fragile state where particles act in perfect unison. In the warm, wet environment of the brain, maintaining such coherence seems impossible, yet some researchers propose it could occur in sheltered regions within neurons. If so, vast networks of neurons could act not as simple switches, but as coordinated quantum systems, processing information in a holistic, non-local way. This could explain the brain's remarkable efficiency, solving complex problems with a speed and intuition that would overwhelm any classical computer. Another piece of the puzzle is quantum tunneling, the bizarre ability of particles to pass through energy barriers they should not be able to cross. This phenomenon could be at work in the synapses, the tiny gaps between neurons where communication happens. Neurotransmitters, the chemical messengers of the brain, might employ quantum tunneling to cross the synaptic cleft with impossible speed and precision, allowing for the near-instantaneous coordination that underpins a flash of insight or a complex physical movement. But perhaps the most profound implication touches the very core of our humanity, the question of free will. If our brains were purely classical, deterministic machines, then every thought and decision would be the inevitable outcome of prior physical states, a chain of cause and effect stretching back to the beginning of time. True freedom would be an illusion. Quantum mechanics introduces an element of genuine, irreducible randomness into the universe. If this quantum randomness is harnessed by the brain, it could provide the necessary escape from pure determinism. Your choices would not be the predictable output of a biological computer, but could involve a spontaneous, non-algorithmic leap. This is not randomness in the sense of a coin flip, but rather a creative source of genuine novelty, where the mind selects from a menu of possibilities presented by quantum events. In this view, your free will is not a ghostly force violating physical law, but a sophisticated biological capacity to amplify and channel quantum indeterminacy into meaningful, deliberate action. You are not a clockwork puppet, but a quantum conductor, orchestrating the inherent spontaneity of the cosmos into the unique melody of your own life. This dizzying regress of simulations shatters any remaining sense of a solid foundation. If our reality is a simulation, what is stopping our creators from existing within a simulation themselves, and their creators within another, in an infinite, dizzying cascade of worlds within worlds? This is the simulation within simulation possibility, a hall of mirrors that stretches into an endless computational abyss. The computational power required for such a nested reality is almost beyond imagining. Each layer of simulation would need to model not only its own universe, but the entire computational substrate of the universe one level below it. It would be like a computer inside a video game powerful enough to run its own, equally complex video game, and so on forever. This seems to demand infinite resources, a logical impossibility, yet there is a potential escape clause. Each subsequent simulation might not be a perfect, one-to-one replica of its parent universe. The creators could be using drastic shortcuts, simplifying the physics, reducing the resolution, or only simulating a small, localized region in high detail. Much like a video game only renders the parts of the world the player can currently see. We might be living in a vastly simplified reality, a budget version of a higher universe, and we would never know because it is the only reality we have ever experienced. This infinite regress leads to a philosophical vertigo. If every reality is simulated within another, then there is no base reality, no original cosmos. Everything is a copy of a copy with no authentic source. Purpose and meaning become untethered, floating freely in an endless sea of simulation. Why would any civilization create such an intricate chain of worlds? Perhaps it is for entertainment or research or as a form of cosmic art. Or maybe, in a universe with infinite time and resources, it is simply something to do. The most haunting question is whether we could ever detect our place in this cosmic stack. One tantalizing clue might be found in the very fabric of our physics. If our creators are taking computational shortcuts, we might find evidence of those optimizations. Perhaps there is a fundamental resolution to space, a pixelation at the smallest possible scale. Maybe the speed of light is not a fundamental constant, but a processing limit, a maximum clock speed for our cosmic computer. Finding such artifacts in our laws of physics would not only suggest we are in a simulation, but that we are in a simulation that is itself being simulated, a telltale sign of a universe built with finite resources. We are left peering into an infinite recursion, wondering if we are the dreamers, the dream, or merely one reflection in an endless corridor of mirrors. The relentless rise of entropy might be the engine driving time itself. The second law of thermodynamics states a simple, brutal truth for the universe, that the total disorder or entropy of an isolated system always increases over time. A cup of hot coffee cools to room temperature, its heat dissipating into the air, never spontaneously gathering back into the cup. A sandcastle is washed away by the waves, its intricate structure returning to the random grains of the beach. This irreversible slide from order to chaos seems to define the arrow of time, giving us a clear direction from past to future. We remember the past, a state of lower entropy, and we anticipate a future of higher entropy. But is this flow a fundamental property of the cosmos, or is it a spectacularly large-scale statistical illusion? The laws of physics, from Newton to Einstein to quantum mechanics, are almost perfectly symmetrical in time. If you were to watch a film of two planets orbiting each other, you would be hard-pressed to say if the film was running forward or backward. The equations work just as well either way. The arrow of time emerges not from the fundamental laws, but from the specific, low-entropy boundary condition of our universe at the moment of the Big Bang. The universe began in a state of incredibly low entropy, an exceptionally ordered and smooth configuration packed with immense energy. It was like a perfectly stacked deck of cards, a wound-up spring, a pristine egg before it is scrambled. Since that initial moment, the universe has been doing what all systems do. It has been evolving toward a state of maximum probability, which is a state of maximum disorder and uniform temperature, the eventual heat death. Our experience of time's flow is our journey down this cosmic slope, from that improbable beginning toward an inevitable, featureless end. Your own consciousness is caught in this current. Your memory works because it requires a permanent change in your brain, a one-way process that increases entropy. You can remember the past but not the future because the past is the state of lower entropy that left a mark on you. This raises a profound question. If the arrow of time depends entirely on that initial low entropy state, then why did the universe begin in such a special, ordered condition? Was it a mere accident, a single, random fluctuation in an eternal, chaotic void? Or does it point to a deeper law of cosmology we have yet to understand? The thermodynamic theory of time suggests that the flow you feel so deeply is not written into the fundamental fabric of reality, but is a grand, emergent consequence of our universe's singular and mysterious starting point. Category theory offers a different kind of map for reality, one that ignores what things are made of and focuses entirely on what they do and how they connect. This abstract branch of mathematics suggests that the true essence of the universe may lie not in the fundamental particles or forces, but in the web of relationships between them. In this framework, the most important thing about an object is not its internal structure, but the pattern of how it interacts with everything else. Think of a social network. The importance of a person in that network is not defined by their height or their job title, but by their connections, their relationships to friends, family, and colleagues. Category theory argues that physics should take a similar approach. An electron is not defined by some mysterious inner substance, but by how it relates to photons, how it interacts with other electrons, and how it responds to electromagnetic fields. The relationships come first, and the objects themselves are almost secondary, defined entirely by their place in the cosmic web. This represents a profound shift from traditional mathematics, which is largely built on set theory, a language of containers and their content. Set theory asks what is inside the box. Category theory ignores the box entirely and asks only how this box transforms into that box and what patterns those transformations create. It provides a language for talking about processes, changes, and connections in their most pure and general form. Because of this, it has the potential to unify seemingly disconnected areas of physics. The same categorical pattern that describes the quantum entanglement of two particles might also describe the way space-time curves in the presence of a massive star. It hints at a deeper relational logic underpinning all of existence, a grammar of connection that could be the ultimate language of reality, revealing a cosmos where being is defined entirely by becoming. The equations endure long after the theories they once described have faded into history. This is the quiet promise of structural realism, a philosophical anchor in the turbulent seas of scientific progress. We have watched grand theories rise and fall, from the celestial spheres of Ptolemy to the luminiferous ether of the 19th century. Each was believed to be a true picture of the world, and each was eventually discarded. This pattern of overthrow can make science seem like a parade of failed ideas, leading to a skeptical view known as anti-realism, which suggests our best theories are merely useful instruments for prediction, not descriptions of a real world. Yet, structural realism proposes a compelling middle path. It argues that while our specific pictures of reality are often wrong, the underlying mathematical structure those pictures try to illustrate survives. The relationships captured by the equations persist, even when our mental image of what is relating to what gets completely revised. Consider the transition from Newton's theory of gravity to Einstein's. Newton pictured gravity as an invisible force acting instantly across space, a tug between masses. Einstein replaced this with the mind-bending concept of curved spacetime, where gravity is not a force but the geometry of the cosmos itself. The picture changed dramatically, yet the mathematical structure of Newton's equations did not vanish. They remain an incredibly accurate and essential approximation of Einstein's equations for most situations in our daily lives. The structural relationships between mass, distance, and acceleration were preserved, embedded within a more profound and accurate framework. It is as if science is an explorer mapping an unknown continent. The first maps are crude and filled with errors, showing sea monsters where there are only waves. But the relationships between the landmarks, the distances and angles between the capes and rivers are often surprisingly correct. As the maps improve, the monsters vanish and the coastlines become more precise, but the fundamental network of connections, the structural skeleton of the land, was there from the beginning. This is not just about gravity. Look at the evolution of our understanding of light. We once thought it was a particle, then a wave in a mysterious medium, and now a quantum object that is both and neither. Through every revolution, however, the mathematical relationships describing how light behaves, how it reflects, refracts, and interferes, have remained robust and true. The structure of its behavior is the constant. Our story about its nature is the variable. This view offers a hopeful vision of scientific knowledge. We are not just building castles of ideas that are doomed to collapse. We are slowly, painstakingly uncovering an enduring structural blueprint of the universe, a relational tapestry that remains true even as our perspective on it endlessly deepens and transforms. The solid world around you may be a magnificent illusion, a secondary reality emerging from a far deeper layer. The informational universe hypothesis proposes that the most fundamental ingredient of existence is not matter or energy, but information itself. In this radical view, every particle, every force, and every law of physics is a manifestation of information processing. The universe is not a collection of things, but a vast, dynamic network of data and computational relationships. This idea was powerfully captured by physicist John Wheeler with his famous phrase, "it from bit." He suggested that every particle, every field of force, even space-time itself, derives its function, its meaning, its very existence from answers to yes or no questions, from binary choices, from bits of information. The chair you are sitting on is not fundamentally a solid object. It is a stable, consistent pattern of information, a dense network of bits that your senses interpret as solidity. Its color, its texture, its weight are all informational outputs from this cosmic computation. Modern quantum information theory has taken this seed and grown it into a formidable framework. It treats quantum states not as physical waves but as units of information known as qubits. Unlike a classical bit, which can only be a 0 or a 1, a qubit can be both at the same time, a superposition that allows for a staggering density of information. The strange phenomena of entanglement, where particles remain connected across vast distances, is reinterpreted not as a spooky force but as a perfect correlation of information. When two qubits are entangled, the information describing them is shared, not localized to either one. This perspective elegantly reframes the nature of reality. The laws of physics are not written in stone. They are the emergent software of the cosmos, the consistent rules that govern how information is processed and transformed. A black hole, once thought to be a destructive pit, is now seen through this lens as an object with a maximum possible information density. Its event horizon a boundary that encodes everything that falls within it. We are not just made of stardust, we are made of cosmic code, living in a universe that is less a great machine and more a great computation, perpetually calculating its own existence into being. A single, unified experience of the color red is a reality no computer can simulate. This is the profound puzzle at the heart of our final theory, Giulio Tononi's integrated information theory. It offers a bold, mathematical framework for consciousness, suggesting that it is not merely a byproduct of complex computation, but a fundamental property of any system that possesses a specific kind of causal power. The central idea is integration. When you look at a red apple, your brain does not process the color, shape, and texture in isolated modules. These elements are woven together into a single, indivisible experience. You do not see disembodied redness and a separate roundness. You see a red, round apple. This unity is the hallmark of consciousness. Tononi captures this with a precise measure he calls phi, a number that quantifies a system's capacity for integrated information. Phi measures how much the whole system knows that is not reducible to the sum of its parts. Think of a team of experts. If each person works in complete isolation, the group's total knowledge is just the sum of their individual expertise. But if they collaborate, sharing ideas and building on each other's insights, they generate a new, emergent understanding that no single member could have achieved alone. The team has high integration, a high phi. Your brain is the ultimate collaborative team. Its billions of neurons are so intricately interconnected that the information they hold is fused into a unified whole, giving rise to your rich, singular stream of awareness. This leads to a startling conclusion. Consciousness is not an on-off switch, it is a spectrum. A human brain has a high phi, while a simple thermostat, which merely switches on and off, has a phi close to zero. It may process information, but it does not integrate it into a unified experience. Integrated information theory makes even more radical claims. It implies that consciousness is substrate independent. It does not matter if the system is made of neurons, silicon chips, or any other material. If it has the right causal architecture to integrate information, it will have some degree of conscious experience. A sufficiently complex and integrated computer network would not just act intelligently, it would feel like something from the inside. This theory reframes our entire reality. Perhaps the universe is not built of mindless matter, but is instead a vast hierarchy of systems with varying levels of phi. A galaxy, with its complex gravitational interactions, might possess a faint cosmic glimmer of awareness, while a human being possesses a vibrant, focused consciousness. We are not separate observers in a dead universe, but localized peaks of integrated information, temporary eddies in a cosmos that is, to some degree, feeling its own existence. Your mind is not in your brain. Your mind is the specific, irreducible way your brain integrates the world. If consciousness is truly a fundamental feature, then the universe itself might be stirring with a deep, slow form of awareness. Integrated information theory does not limit experience to complex brains. Any system with some degree of integration, with a phi value greater than zero, possesses a sliver of consciousness. A simple photodiode, a device that converts light into an electrical current, has a tiny, almost negligible phi. Its experience would be unimaginably simple, perhaps a single, isolated bit of feeling, a faint hum of existence when light strikes it. A thermostat, with its basic on-off states, might have a slightly richer but still incredibly primitive inner world. This is not the romantic panpsychism where rocks are happy or sad. It is a colder, more mathematical claim that even the simplest causal structure has an interior perspective, however dim and elemental. This elegantly reframes the hard problem of consciousness. The question is no longer how subjective experience magically emerges from unfeeling matter. The problem is inverted. Consciousness was always there, in every scrap of causality. And the real mystery becomes how these micro-experiences combine and orchestrate themselves into the vast symphonic stream of your own mind. Your rich awareness of a sunset is not built from nothing, but from the integration of countless simpler conscious moments happening within your neural circuitry. The universe, in this view, is not a dead mechanical void. It is a vast and layered spectrum of sentience, from the faint whisper of a spinning electron to the roaring symphony of a human brain. This leads to a breathtaking and perhaps unsettling possibility. Could the cosmos as a whole, with its impossibly complex web of gravitational, quantum, and informational relationships, be a conscious entity in its own right? Its phi value would be astronomically high, though its experience would be nothing like our own. Its thoughts would be the slow dance of galaxies, its memories written in the cosmic microwave background, its perceptions spanning billions of years. We would not be mere inhabitants of this cosmic mind. We would be tiny, fleeting nodes within its vast neural network, momentary flashes of focused awareness in a universe that is itself awake. From the stark certainty of materialism to the cosmic dream of idealism, our journey has spanned 50 visions of existence. We have stood before the possibility of a simulated reality, walked the branching paths of the many worlds, and peered into the pixelated heart of a holographic cosmos. We have seen time as a frozen block and as a flowing river, and questioned whether the universe is a grand computation or a symphony of pure mind. Each framework, from the mathematical universe to biocentrism, offers a unique window into the profound mystery of why there is something rather than nothing. They are not merely academic exercises, but radically different ways of being in the world, each reshaping our understanding of life, death, and our place in the grand scheme. Yet, for all this dazzling diversity, a single, humbling truth remains. The ultimate nature of reality continues to elude our grasp, a shimmering horizon that recedes with every step we take. This is not a failure, but an invitation to perpetual wonder. So we turn this final question over to you. Which of these 50 theories resonates most deeply with your own experience of being alive? Does the block universe comfort you, or does the participatory universe ignite your imagination? Share your perspective and keep the conversation alive, for in questioning the fabric of reality itself, we engage in one of the most human endeavors